This presentation will introduce a new tool for the conceptual design of structures in equilibrium based on graphic statics. This contribution is the result of an ongoing collaboration between Yuchi Shen from the Southeast University of Nanjing, Pierluigi from the Technical University of Munich, Jean-Philippe Jasienski from UC Louvain, and Patrick Ohlbrock from ETH Zurich. As shown by these two examples of the Salginato Bell Bridge by Robert Maillard and the Hungarian Orbetello by Pierluigi Nervi, graphic statics is a powerful tool for conceptual structural design. Graphic statics is grounded on the use of two diagrams, the form diagram and the force diagram. The form diagram shows the geometric layout of a loaded structure and the forces applied to it. The force diagram represents the equilibrium of the forces within the structure. Through these two diagrams, with graphic statics, it is possible to design structures controlling form and forces at the same time. Over the last few years, thanks to the developments of computer-aided design and the emergence of new parametric digital tools, graphic statics has experienced a revival at both professional and academic levels. In 3D graphic statics, for a given 3D form diagram, like the self-stressed tetrahedron that is shown in this slide, two alternative versions of force diagrams can be constructed, the polyhedron-based and the vector-based. The computational tool that we will present in this presentation is based on the vector-based approach. Vector-based graphic statics was originally described by Maxwell. In this approach, form and force diagrams are made out of closed cycles of vectors. For a given structure in static equilibrium regarded as a form diagram F, a vector-based force diagram can be built node by node. In this case, like in traditional 2D graphic statics, vectors parallel to the bars concurrent in one node can be scaled so that they generate themselves as closed cycles of force vectors. After repeating this construction, for every other node of the structure, a series of closed cycles of vectors, also known as force polygons, can be generated. These cycles can be then assembled into one unique force diagram made of vectors. As explained later, in the general case, for a given form diagram, multiple configurations of the force diagrams can be generated. By implementing this approach into a computational tool, the relationship between form and force diagrams can be used for the real-time transformation of the structure. In this way, the geometry of one of the diagrams can be modified while assessing the consequent transformation of the other diagram.
The general procedure of the computational implementation of vector-based graphic statics is as shown on this figure. First, a form diagram F is generated from structural geometry and a set of forces. At the same time, two procedures are carried. On one end, the equilibrium solver determines the intensity of all the forces in the structure, and on the other end, an algorithm determines the assembly sequence for the forces. These two sets of data are used in the assembling procedure that assembles the nodal force polygons into one complete force diagram. Afterwards, transformation of both diagrams can be done. The two interdependent form and force diagrams are modified according to the transformation that is carried on the other. Now, let's have a closer look at the algorithm that finds the assembly sequence. First, the form diagram is converted into a non-directed graph. Then, the user can choose one of the three developed algorithms to planarize the graph if it is not planar, which means it contains crossing edges. The resulting plane graph is embedded, and thanks to this, a list of ordered nodes for each vertex of the graph can be extracted. This list will be used for the assembling procedure. Now we'll briefly overview the result of the three planarization algorithms for the same self-stress structure. The cycle method is the closest one to the theoretical one. The planarization process consists in starting from the full topological graph and splitting edges and reconnecting them to the one or more new cycles until planarity is achieved. The two other polarization algorithms conceptually work the other way around than the one introduced previously. Instead of removing edges from the initial graph to make it planar, it starts from a planar subgraph that is successively enlarged to correspond to an acceptable plane graph. The quad procedures always generates quads. Like the cycle method, the MED method is based on the splitting procedure that is explained in literature. It successively adds back edges to the reduced planar graph with the simplest splitting configuration. These three methods provide different typologies of force diagram for the same form diagram.
This is an outline of VGS plugin based on the Rhino Grasshopper platform. VGS contains three parts. The first is generating equilibrium and interdependency. The second is transforming equilibrium based on the interdependency of form and force. The third is the real-time displaying and analyzing. In the first part, VGS provides a general solver for the strong and time model based on the equilibrium matrix method. This algorithm facilitates users to calculate the normal stress and the determinacy of a configured strong and time model. Meanwhile, VGS also provides an interface connection with other equilibrium solvers, which means users can also input equilibrium structural configuration from CRAM3D, CEM, Peregrine, and other related solvers. Once the form diagram is obtained, it's time to generate corresponding force diagram with different approaches. These approaches are all based on the planarization method and the sequential assembling algorithm we developed with the feature from NetworkS library. So the interdependency between form and force diagram would be established in this step, and we can verify this by seeing each node in the form diagram corresponds to a closed vector polygon in the force diagram. In the second part, based on the solved form and force diagrams, VGS enables users to manipulate form and force diagrams by employing dynamic particle systems from Kangaroo library. The users are able to set geometric goals and constraints based on the specific design intention, and because of the fixing interdependency between the two diagrams, all the transformed solutions are kept in equilibrium. In the third part, VGS provides a powerful real-time displaying system with which the solutions can be shown and evaluated in different ways while structure exploring. In addition, the built-in statistical tool helps to show the numerical status of the structure. VGS provides a complete workflow for users to do both the aesthetic-oriented and performance-oriented form finding in the conceptual stage of design.
In the last part of the presentation, we're going to apply the VGS tool to a case study. In this case study, the fictitious design task is to design a new roof for the Ullevi Stadium in Gothenburg, Sweden. The following video shows a possible integration of VGS in the conceptual design phase. The idea is to design a spoke wheel system that follows the characteristic undulation of the bowl and at the same time creates more cover than the existing roof. The target curves for the tension and for the compression ring on the outside. In this case study, we actually focus on the form finding of a quarter of the stadium that you see here, through making sure that the forces at the interface between two quarters are always perpendicular to the corresponding mirror plane that you see here. In the first step of the video of the process, we actually use the combinatorial equilibrium modeling to set up the form finding problem. We have to describe the topology as well as the metric parameters involved in that problem. Then we can use the algorithm of the CEM to get the first equilibrium state that you see here in red and blue. You see the tension ring, you see the compression ring as well as the spokes. Then through an adaptation of the inner force of the spokes, for example, we can manipulate in real time the equilibrium form that you see here and actually already make sure that the curves in equilibrium are already quite close to the target curves that you see still in black. This information that we get here can then be translated into the transferred to the VGS tool that you see here. What we have to do is we have to take the information of the geometry as well as the inner forces, and we have to obviously also give information about the loads, about the external loads that are in this case the forces at the parameter of the corresponding rings as well as some vertical forces at the compression ring that we allow. Then we can press the button to assemble the force diagram. You see it here. And after a short moment, you see actually the form diagram that corresponds to the form diagram of the CEM. But you see now also the force diagram that you see it here at the bottom of the stadium visualized. In the next step, we can start formulating constraints in order to transform this equilibrium state. The first constraint is the perpendicularity that I mentioned in the beginning, to make sure that the forces are perpendicular. Then we introduce some geometric constraints to make the nodes of the compression ring match the target surface that you see in green, that is derived and connected to the black target curve. There's a certain extrusion that we see similarly here in the tension ring that has more degrees of freedom in the Z coordinate. On top of these two geometric constraints, we also formulate another geometric constraint actually to make sure that the length, the segments of the tension and the compression ring stay more or less the same. You see here for the tension ring, here you see it for the compression ring, and then we actually also add one constraint to the force diagram, in which we want to make sure that the forces in the spokes are staying more or less the same intensity. Translated into the world of geometry, that means that they also should have the equal length in the force diagram. Important to notice that you can have different strength for each of these constraints and also guide the convergence in different directions, obviously. Then in the next step, we use VGS together with Kangaroo 2 to transform this equilibrium state. What you see here, actually we have then a new instance of a form in the force diagram. Here you see already a transformed state, but once I press the run button, you can see, and the reset button, you see how it is transforming from an initial state to the converged state. You see here the convergence. You can observe how the form and force diagram are both changing simultaneously in order to match the given constraints as close as possible. You can obviously let it run very long or very short. It's up to you as a designer to also see when it fulfills the requirements. And in this case, actually, we take this form found quarter and modify it. We replace the spokes now with each spoke with 4 cables and 1 flying column that you will see in a short second. Before this, I turn off the form and force diagram visualizations and not to have too many diagrams overlapped. Now we have an empty canvas, and we can activate the new form diagram and the new force diagram. You see it here, actually a little bit more complex, where we now have also some additional struts, vertical struts that we also see in the force diagram. Now changing the height of the flying columns will also have an effect obviously on the force diagram, and I can also, for example, change the position along the spoke that you will see here. I can bring it to the very inside here and will have a dramatic effect on the force diagram, bring it more to the center, and see accordingly how the form and force diagram will change. So now we actually have a form found the quarter of it, and now I can start extrapolating it and see how the full stadium roof would look like. You see it here. Now if I turn it off, you can also go one step further and use Caramba 3D, for example, to make a more systematic analysis also in terms of other load cases. You see here, what is quite nice is that the section forces correspond quite well to what we have envisioned with our form finding. You see now that the inner ring is fully in tension. Now the color code switched from blue to red, but it should follow exactly what we have in mind in our conceptual design here.
As a conclusion, this video introduced VGS, a new computational tool for the design of structures at equilibrium.